Okay, so today we're going to talk about distributed consensus. This is the other thing that you need in a blockchain. So we talked about all the cryptographic underpinnings to get authenticity, to get immutability. But now we need to get people to agree on a particular state. We need to also make sure that that state is available everywhere. And in order to do this, we need replicas, and we need some kind of consensus algorithm to agree that the replicas, which replica we're going to use, the state of the replica. So this is the distributed consensus problem. So to motivate this, we're going to look at a rogue blockchain. So we're going to go to this link. You can click on it right now if you'd like. There are 3 peers with 3 versions of the blockchain, and they start out exactly the same. But if you have a node who wants to sort of create its own blockchain, maybe a nefarious node, and wants to add transactions onto his or her blockchain, but that aren't on the other 2, then how do you reconcile the fact that your peers might have differing versions of the blockchain? So, for example, you could have, this is the distributed blockchain. You have peer A, whoops, you don't have that. How do I get that? One second. So if you go to that link, you'll see that peer A has a particular version, and if you look at the hash, the last hash is 4 zeros and a B. Same with, you start out with B, has the exact same, and same with C, has the exact same blockchain, but what you want to prevent is someone from injecting data, mining it, or taking a different subset of transactions. So they can't necessarily break the authenticity thing without breaking public key cryptography, but they can collect up a different subset of valid transactions and try and shift the blockchain state towards their version of reality. And so that's what I'm trying to do with B. B is taking a different subset of transactions and saying, this is my state. This is my ground truth. And it might be different than the other 2. And so if B decides to take a different set of transactions and decides to mine the chain, you can see that B will end up with a different blockchain state than the other 2 as soon as this finishes. Wow, that's taken a long time. Oh, and I have to do the other 2. Okay, so it's going to make me do all of them. So then you'll end up with valid blockchains for these peers that are different. All right, so that's the problem. So that is 4 zeros E4B, and this is 4 zeros 49B. So how do you choose? Now you have 2 different versions of valid blockchain state. How do you choose between them is the distributed consensus problem. Okay. Okay, so that is the consensus protocol that we're looking to solve. So consensus, distributed consensus is agreement on state, including the exact ordering of events, in the absence of a trusted central authority. If you had a trusted authority giving you order, then you would just ask that trusted authority for the state. But this is an absence of that. You have everyone is a co-equal participant, so then you would need to be able to, amongst those participants, get a valid state. And this is what, this is important for a distributed ledger like Bitcoin. Okay, so this is a fundamental design choice for any kind of blockchain that you'll see out there, either permissioned or public. Okay, so when we talk about consensus protocols, the consensus protocol needs 2 things. The first thing is it needs safety. So safety refers to consistency. Everyone has a consistent view of the state. They're all the same. And correctness. There are no invalid sequences of transactions in the log. So that's what these two things are. Guaranteed same state. And then the algorithm is such that the transactions in that log will basically behave identically to a single node system that executes each transaction atomically one at a time. This is an ordering property. The other thing it needs is liveness. So each non-faulty node will eventually receive every submitted transaction. That it will continue to make progress as long as it doesn't have a fault. That you'll keep the thing updated. Okay, so the original work in this topic goes back to 1978. It's not something that we teach a lot in this curriculum. We don't teach a lot of distributed systems. But if you do want to understand distributed systems, pretty much you would have to go back to 1978 to the start. This is Leslie Lamport's Time Clocks and Ordering of Events in a Distributed System. And this is a seminal paper on how do you achieve ordering of events when the events are distributed, right? And then you have message passing, and you have messages that have delays, you have messages that are dropped. How do you figure out what events happened in what time, at what order, amongst a bunch of distributed processes? This is a really hard problem. The first thing that Leslie Lamport does is he proves that strict consistency, a total ordering of events, requires absolute global time, like completely synchronized clocks in order to do this, and that's impossible. We can't synchronize clocks to a global time state. I don't know much about quantum physics, but I'm guessing that that still hasn't happened. But that's basically why this is considered impossible. And so he defines a looser kind of consistency. He defines causal consistency to define event ordering. And so the causal consistency paradigm means that all of the writes that are related to each other, that are causally related to each other, have to have a total ordering. The ones that can happen in any order and not change the final state, those are not causally ordered. So if I have two independent requests and it doesn't matter which order they happen in, they can be, or they don't impact the final state if they're in different orders. Those can be completely unordered. But if I have sequential writes to a file, I need to have a strict ordering of those writes, because if I give those in different orders, I'll end up with an inconsistent file at the end for certain people. One person will get one kind of file, and the other person will get a different version of that. Okay, so how does this protocol that he proposes do this? He uses communication events on a particular node to establish an ordering at that node. So this is a partial ordering system where receive events on communication messages for a particular node are timestamped. And then these logical timestamps provide you an order, so the communication receives and the communication sends on a particular node are logically timestamped with that node ID and that event ID. And that event ID monotonically increases. And then for at least the one node, you can have ordering of messages. And on another node, the send and receive events from that particular node are being, so that node is sending a bunch of timestamps, logical timestamps, to anyone that it communicates with. And those nodes will also receive those logical timestamps and be able to order their events based on that. So the synchronization of ordering is done by the message passing. Okay? And this is much easier to achieve versus strict consistency. Okay. So the paper describes how you get consensus. You get causal consensus on causally consistent events without synchronized clocks. So that's what this thing required up here. Strict consistency required synchronized clocks. But this thing doesn't require synchronized clocks, but the protocol only works if there are no faults in the network. Yes. It's a node ID and an event ID that monotonically increases so that you can actually get the order of events on that one node. And because those timestamps are sent across the network, you can get causal consistency of that node's events into the other node. Yeah. So I'm not going to go through the details of this. It would gloss you over pretty quick. But that's the take home is that there is a way to get this causally consistent consensus without the synchronized clocks, but it does assume there are no faults. Because as soon as you start to have faults in the network, you have difficulty making progress in the consistency. Okay, there are other kinds of consistency that are defined in this paper. There's a notion of sequential consistency, which focuses more on the result. The thing is sequentially consistent if an execution through the transactions will produce the exact same result regardless of the ordering within that. So this is a result-focused consistency. There's another kind of consistency, and this is the consistency that the DNS system that we use on the internet does, is that eventual consistency. So eventual consistency says if there are no longer any more updates to the system, the state that everyone gets will eventually be the same, right? So this is also focused on the result, that eventually everyone gets the same state, okay? So after Lamport produced this paper, they were looking at a bunch of theoretical results on how it is we can get consensus in a distributed system. And then the seminal work on proving this to be impossible under certain conditions was this FLP paper, Fisher, Lynch, and Paterson. And they proved that the consensus is impossible in an asynchronous network. And in asynchronous, it means that the messages can have unbounded delays with a deterministic protocol. So this is the result that you'll see pop up over and over again. So there is this trade-off between liveness and consistency, and you can't have both, is the take-home point here. Okay? Especially in the presence of failures. So liveness, consistency, and failures, they're all tied together. So from the cloud class, this is, if you take the cloud class, this is directly related to what we cover related to the CAP theorem. So the CAP theorems, the CAP means consistency, availability, and partition tolerance. And this is related to distributed replicated databases, which is basically what a blockchain is. So these results are very similar. The CAP theorem says you can have 2 of the 3 properties in a replicated distributed database, but you can't have all 3. Right? You cannot be consistent, be highly available, and tolerate partitions in your network all at the same time. You have to choose 2 out of the 3, and it's the same kind of choice that the FLP impossibility result is giving you. So when you're designing an algorithm, you're governed by this stuff, these 2 things, which from what I can tell, still are valid. No one has proven otherwise. It's not like the P, well, sort of like the P and NP thing. Okay, and you can sort of intuitively think about this, right? Like I'm trying to get agreement across my entire network, and what happens if I'm partitioned from half of it? Like how do I get that other half to also agree on my state? Well, that's going to require me to either become inconsistent or to freeze progress. So that's the consistency versus availability, okay? So that's the groundwork. We're going to talk about different ways of achieving consensus. And the first class of algorithms we're going to talk about are the non-Byzantine consensus ones. And these are really complex, but this is addressing the easier deployment of a consensus protocol. The main ones that are being used underneath are Paxos and Raft. So the motivation comes from a question, and the question this is also from Lamport, was can you implement a distributed database that can tolerate the failure of any number of its replicas without losing consistency. So that's a big thing in databases. And will resume normal behavior when more than half of the replicas are again working properly. So this is the problem he formulates, because this is really important for distributed databases. If you want a globally consistent replicated database on the internet for whatever service you're producing, maybe it's a banking app, maybe it's a gaming app, you want this property. And so in 1989, he writes this paper, The Part-Time Parliament, and it's a replication protocol for distributed systems, and he uses this fictional Greek island called Paxos, which is why the system is called Paxos. And it has a part-time parliament, so this parliament likes to go on vacation, and those vacations are not synchronized, right? And a whole bunch of these legislators are going on vacation at any point in time. So the lawmakers come and go frequently into the forum. The goal is to keep a consistent replicated ledger containing all the laws that have been passed. And it has to be kept in a distributed fashion. Every lawmaker will eventually get a consistent set of laws. If a majority of the legislators are present for a sufficient time period, then any decree that has been proposed by a legislator will be passed and entered into the record. And then every decree that has been passed should eventually appear in the ledger of every single legislator in the chamber. So the replicas can come and go, but eventually everyone gets a consistent ledger of all the laws. And you'll see that this is an abstraction that's really powerful in computing systems. So for example, if you store stuff in the cloud, so Google Cloud Storage is this replicated and consistent storage backend that Google is using everywhere. You would like copies of that to be everywhere, but disks are going up and down all the time, right? And you want to be able to guarantee that eventually everybody, every replica in your cloud storage bucket has the same state, has a consistent state, okay? So Paxos is this algorithm that supports this. It gives you strong consistency in the presence of crash faults. All of the state changes are eventually seen by all of the distributed processes, and you can think of this as all the lawmakers. So each lawmaker is a process. And it's seen in the same order. So that's what the algorithm, the magic of the algorithm allows you to get, okay? So it does this with a consensus protocol that avoids blocking in the presence of any single failure. So it's tolerant to single failures. Okay, and it's provably correct if n processes want to agree on a value. Then it is provably correct as long as a majority of nodes are still working. So this is what this constraint is. The total number of nodes that are in the system has to be greater than twice the faulty nodes plus 1. So that means the non-faulty nodes have to outnumber the faulty nodes. And then you can make progress and achieve consistency using this algorithm. Okay? So Paxos in the FLP result, it chooses consistency over liveness in an asynchronous environment. If you have the number of legislators is not a majority, then you basically you lose liveness. You can't pass laws. But as soon as you have the number of lawmakers, you can start progressing in a consistent manner. You can actually get that state to start replicating to all the live nodes. Okay. And this is from the Paxos.systems, and this website is hilarious because it says Paxos rather than Paxos made simple. It's titled Paxos made moderately complex. This is a really complex protocol. To actually get this abstraction, there's a lot of message exchanging and voting and group organization and quorum making that has to happen in order for this to actually work. This is a quote from that site that talks about the FLP impossibility result, and their choice is to always choose consistency over that liveness. And this makes sense, right? Because if I have a file stored in my bucket and because of your replication system it loses its consistency, that service is useless to me, right? I would much rather be disconnected from my bucket than for you to corrupt my data on the back end, okay? So the progress is blocked until a majority is present. And hopefully that makes sense to you intuitively. I'm not going to teach you the actual protocol. Well, I'll show you a picture of some of the message exchanges that are going to go on with these protocols, but that's not really the point of this class. So this is the idealized version of what Paxos is doing. It's similar to the marriage protocol. So the client is proposing a write to this leader, and the leader is sending a prepare message to the acceptors. So this is a proposed state change, and the leader's like, hey, I want you to commit to this state change. So do you commit to this state change is this question to the acceptors. And then the acceptors will come to an agreement and say, yes, I do. And then when those messages are agreed upon, it does the commit. So this is part to get the consistency, because you have a whole bunch of these events going to the leader. The leader is saying, this is the state that I want to commit to. And if all acceptors agree to it, then this is their final thing that says, that is the next block, or that is the next update that I need to commit. So it's this two-phase commit protocol. And you'll see this in databases and in any sort of distributed system. This multi-phase commit allows you to make sure that you have a consistent state. So this part is for the consistency. Okay. Okay. This is a picture from the site that talks about the commit phase and the proposed phase and the commit phase. So this is just a flow chart of the sequence of messages on the back end to achieve this consistency. Okay, so I want to bring up that this underlies just about all of the distributed systems that you'll see out there. So on Google, it's in Spanner, it's in Bigtable, it's used in a lot of the Apache project, the replicated databases on the back end. It's used in Hadoop, it's used in Kubernetes, it's used in ECS, which is Amazon's container service. The problem comes up over and over again, and these are the Paxos and Raft are the things that they're using to solve these problems. Okay. Raft is another system that's similar to Paxos, but because Paxos was so a little bit of history, and this is in the extra slides that I skipped. Paxos was proposed, when was it? This was in 1989. The paper was rejected, and it was so complex that nobody tried implementing it until like 1995. And then finally, some of these infrastructure providers started implementing it, and then they realized that this was actually something useful. So this paper actually got published in 1998. So you see this 9-year difference between when it was proposed and when it was actually published. It was because of its complexity and the fact that nobody could understand it, let alone build it, that the thing stayed hidden for like a decade. So that's sort of a funny aside on Paxos. And so the motivation of Raft was to try and make a system that implemented what Paxos implemented, but was actually understandable. And I think so this is the paper from 2013. Well, you can get it from their GitHub. And it's been formally verified for safety, just like Paxos is safe. And it's just like Paxos, a quorum has to exist to make progress. And the mechanism is similar to Paxos. You have a set of leaders that get elected to coordinate the consensus. And then if that leader crashes, so this is a fault-tolerant, it's supposed to handle crash faults. So you need to be able to handle crashes in the leader. And the way Raft handles this is if there is a leader that crashes, then there's another election to elect a new leader in the consensus protocol. And the assumption is that the election timeout is much less than the mean time between failures in order to keep the thing live. So that's one of the properties of Raft. This is a thing that Kubernetes is using. So etcd is this distributed key store state that's consistent, and then this is what Kubernetes uses to coordinate its distributed system. So in the cloud class, Kubernetes is a way of controlling a whole bunch of computing resources automatically. But in order to do that control, you need a consistent state of what is out there, and that's what Kubernetes is. And it's being used to run just about all the backends in modern cloud deployments. Okay, so there's several issues with both Paxos and Raft. They only handle crash failures. So the fault consists of nodes that can be declared dead. Like the nodes will fail closed and basically stop responding. So those are crash failures are easy to deal with, right? You just boot that system out of your protocol, and then you can continue. These protocols don't handle malicious nodes, which are actively trying to inject faulty messages into your protocol. Okay? So for example, what happens if a malicious node is elected leader in both Paxos and in Raft? The leader has specific extra responsibilities, and if that leader is malicious, then you've got a problem in both of these protocols. What happens if a malicious node can corrupt the election process indefinitely? So I mentioned you elect a leader when the leader crashes. What happens if I've gotten into your system and I want to prevent you from making progress by corrupting the election nonstop? Okay. The other thing, so basically, malicious nodes are sort of rare on a back end that you have sort of secured, but on a public in a public environment, so for example in a public blockchain, you cannot be relying on a protocol that isn't resistant to malicious nodes, and that's why you wouldn't see Paxos or Raft in a public blockchain where you can have a malicious participant. Okay, so that's why you'll see these on permission backends, but not necessarily on the public blockchains. Okay, so the next set of protocols we're going to talk about, so that was non-Byzantine consensus. The next set of protocols are Byzantine consensus with strong consistency. And so this leads us to the 1982 paper, the Byzantine generals problem, and this is also from Lamport. And this is a classic problem that you have to solve in distributed systems when the participants can be malicious. So the formulation of this problem is that you have a collection of generals surrounding Rome. Some of the generals are loyal, and some of the generals are traitorous. They're trying to inject faults into the system intentionally. You have a commanding general who wishes to coordinate an attack or a retreat. And then through a series of message exchanges between the commanding general and all the other surrounding generals, you want to come to an agreement so that if the commanding general is loyal, then all loyal generals will obey that commanding general's wishes. Now this problem, as we saw in the previous class, this problem is really easy if you have the general's public key, right? And then the general is signing orders, right? So with public key cryptography, the Byzantine general problems is easy, right? Like you just sign the order, broadcast it, and then everybody with the general's public key can just verify that, yes, this is the commanding general's order. We're going to either attack or retreat. The more interesting problem is with co-equal generals, okay, where you don't have a public key infrastructure and you have equal participants. And this is much more like a public blockchain is, where everyone is sort of treated the same in terms of the participation. So each general, in this case, has a vote to determine whether to attack or not, and the protocol wishes to follow a majority vote. So the majority vote of all of the generals will determine your action. And so the conditions that this problem is seeking to meet are, the first is that every loyal general has to obtain the same value for all of the other loyal generals. I cannot have it be the case that a malicious general can change my vote to the rest of the generals, the loyal generals. So that's the first property. And then if a general is loyal, the value she sends must be used by every loyal general. So this is a similar property. Okay, so here's an animation. So what we want is we have a general G1, and we want G2 and G3 to be able to figure out whether or not G1 wants to attack or retreat. And so similarly, G2 would also run the protocol so that G1 and G3 understand it, and then G3 would run a protocol to get G1 and G2's messages. So for all of the animations in this these examples, we're always focusing on G1, trying to get that general's state, but you can extend it to the other generals. So for non-malicious generals, if everyone is playing by the rules, this is an easy problem. So it's trivial because then you just listen to what G1 sends you. So both G2 and G3 takes the message at face value, agrees to what G1 is doing, problem is solved. So all three of them will then attack. Okay. But you can have a malicious general, and the malicious general can convince disagreement between the non-malicious generals. And so this malicious general can send different messages to G2 and G3. And then in this case, one attacks and one doesn't. You want to be able to avoid this problem, right? Where you can get G2 and G3 to do opposite things. Okay. One of the things you can do to detect that something is going on is to do extra message exchanges. So in this case, if G3 sends a message to G2 saying that G1 told me to retreat, then G2 sees that there are two different messages for what G1 is supposed to do, and it knows that there's a malicious actor. Okay. The question is can G2 determine who is being malicious based on the two messages that it gets? What would be the answer? So the answer is no, because you could have G3 being the malicious actor. G1 is telling both of them to attack, and then G3 says retreat. And then this message view is exactly the same as the other one. So you can detect maliciousness, but you can't do anything about it in this case. You would still have this problem where you don't know if G2 doesn't know if G3 or G1 is malicious. Okay, so Lamport's result and algorithm. The assumption, again, messages aren't signed. Communication is synchronous with bounded delays. And he shows that no solution exists for his algorithm if the delivery times are unbounded. So he is able to achieve consensus using a deterministic algorithm in a synchronous network. And he can do this if and only if the following property holds. The number of total participants has to be equal to 3 times the number of traders plus 1. So basically, this means 2/3 of your participants have to be non-malicious, have to be loyal. And this is a well-recognized result in distributed systems. You need 2/3 of your participants to be non-Byzantine to get this kind of agreement. And there's a polynomial algorithm of message passing that allows you to do this, which we're not going to cover. But I'm going to give you some intuition as to what the protocol underneath is trying to do to figure out consistency. So here is a 4 general solution. So again, we have the number of participants. The loyal participants are more than 2/3 of the total population. So we have this state where, yes, we have more loyal than malicious. And we want G4 to determine the vote that G1 has to either attack or retreat. And we have a malicious participant down here, G3. So G1 says attack. And then each one of these recipients will then forward what G1 told it to do to G4. And of course, G3 is trying to flip the message. And so G3 gets attack and then tries to send retreat to G4. And at this point, G4 sees that there are 2 votes to attack and 1 vote to retreat. G4 can then attack, which is what the original order is. And this is where your additional replication in loyal generals allows you to make the right decision when there's a Byzantine fault, a malicious fault. Here's another solution. If the general G1 is malicious, and you're trying to determine what the majority of G1's votes are, then if G1 says retreat to G4 and says attack to just about everyone else, or the majority of everyone else, then what G2 and G3 will do is it'll send the attack to G4, and then G2 through G4 will all attack, right? Which is what you want. You want the loyal generals to all be coordinated in this case. Okay? So that's the intuition behind the protocol that's running underneath. Okay. Are there any questions about Byzantine agreement and why you need a certain number of replicas to get this thing to work? That's all I'm looking for here. Okay. So this is applied to the real world. Byzantine fault tolerance is everywhere in terms of physical systems, computing systems. This is an example of the Airbus. And the Airbus uses redundancies. So in an Airbus, you need basically 4 copies of every message and of all the buses in order for you to commit a certain piece of state into the control system. And so this is the reason why the Airbus has basically 13,000 pounds of wiring for a 611,000 pound plane. Because all of this wiring to get the redundancy to avoid crash faults and Byzantine faults on an airplane. So this is why airplanes are much safer than you might think. Okay. So one of the things about this protocol is that these Byzantine fault-tolerant protocols always maintain a single, consistent global state. It's always correct, and everyone always gets the same state. And so there are no inconsistencies allowed in terms of one person has one state and one person has another, and eventually they'll reconcile. No, you have one valid state in a BFT protocol, and that is the one everyone has agreed on in sync. So synchronized agreement. Okay, and it's done using rounds of consensus followed by a commitment protocol. So this two-phase commit thing, where there's an initial thing for the consensus, and then you're all agreeing to commit this particular block at the end. Okay. BFT protocols are often made hierarchical. So similar to, for example, internet routing infrastructure is hierarchical. So you allow some local agreement protocol to happen before you then build up to a global commitment. Okay, so this is an approach. BFT protocols are an approach that are being used by all the financial tech blockchains, because you cannot afford inconsistency when you're dealing with monetary transactions on the back end, right? Like, you must have the thing be consistent, otherwise nobody's going to use your thing. Okay, so in this case, these BFT protocols are used because they're always choosing consistency over liveness whenever the thing is partitioned. Like, if you have half of your stuff in Europe and half of your stuff in the US, and you want both of those to be consistent, whenever someone cuts the Atlantic Ocean cables, you will stop trying to make progress on that state until that thing gets reconnected. You're always wanting all of your replicas to agree to one consistent state. Okay? This is completely different than what we'll see with Bitcoin. Okay. There are some issues, though. So BFT protocols have this Sybil problem where, okay, I know all I have to do is get a little bit more than a third to be malicious. So what I'll do is I'll just try and mint identities in your fault-tolerant consensus protocol. And if I can create a number, like, I'll go to Google Cloud and I'll create like 1,000,000 VMs, not 1,000,000, 1,000 virtual machines, and I'll enter your protocol with 1,000 machines, and then I'll do my malicious deed. So as long as I can get more than a third of participants in your consensus protocol, I can win. And this is the reason why most of these BFT systems, participation is set by a central authority or via closed negotiation. There are very few BFT protocols that are running public blockchains. In fact, there's one that I know of, and they have a way of limiting signups, right? Because you always have to make sure you're at least 2/3 non-malicious. Another issue is the complexity of the protocol. There's a lot of message passing going on to figure out what your consistent state is, and a lot of message exchanges. So there's a bandwidth issue, there's a latency issue. All of these issues are a result of trying to solve a complex problem. Most of the algorithms are deterministic and assume synchrony, that there are no, that the message delays are bounded. Okay, so there are alternatives. There are tweaks to the BFT protocols. One tweak are the randomized algorithms. And so we'll go back to FLP impossibility. Consensus is impossible in an asynchronous network with a deterministic protocol. So the idea of these things is to try and solve consensus in an asynchronous network using non-determinism with a probability close to 1. So this, what they're trying to do is to get consensus with a high probability using what we call coin flipping. So this is the coin flipping approach to always make progress in the agreement protocol. And so if you look at the proof in the FLP impossibility result, there's a tiny fraction of bad executions that will result in loss of liveness and will keep you deadlocked, basically. So there are deadlock states in the FLP impossibility result that basically cause this thing to break down using a deterministic protocol. Okay, so if you use random coin flips to make those deadlocks less possible, to make those randomly, to add the randomness in there to make progress all the time, then you can converge using a small expected number of rounds rather than it being deadlocked forever. And keep this in mind for Bitcoin, because Bitcoin also has done some randomization in order to make progress in this case. Okay, so the intuition behind randomized algorithms is that if you have two pedestrians passing each other in the hallway, if you have a deterministic algorithm for deciding which side to choose, then you can get deadlock. And this is exactly what's happening in a consensus protocol if it's deterministic. You can get into states where you're choosing one or the other in synchrony, and then you'll end up deadlocked. So the idea here is that eventually someone will randomly choose a side and stay with it, and then the other person will react and go to the other side. You have a randomized reaction time, basically. Well, usually. You're not live locked there forever, is the idea. There are papers about randomized consensus. I now have a paper list linked off of the website that you can look at for additional reading, if you really like this stuff. There's this paper list, and in this paper list, you'll see this paper by Rabin and Ben Orr somewhere down here. Oh, but I have that linked out if you're interested in reading more about this particular topic. Okay. Okay, another system that was proposed is this DLS consensus protocol in '88. And then this system tweaked the impossibility result by making an assumption on the asynchrony part of this. So in this case, they show that if you loosen this asynchronous part, if you assume partial synchrony, then you can actually make some guarantees on consistency and liveness using a deterministic protocol. So this is the next class. There are two ways that you can loosen the asynchronous assumption with the DLS consensus. The first is that if you know that an upper bound on the delay exists, but it might not be known a priori, you can get a deterministic algorithm to converge by having that algorithm take into account the delays that it sees automatically in its algorithm. So that's what they show. The other result that they show is that there is an if there's an upper bound on delay that will eventually be achieved in the network, then you can also get consistency and liveness. And so the result is if you, on the first two columns are the number of nodes that you need in the protocol for a synchronous assumption and an asynchronous assumption. So this means it's unsolvable, being infinite. But if you have these partial synchrony assumptions, you can then go back to only needing a majority to be non-malicious or needing a 2/3 non-malicious in order to make progress. So that's what this paper talks about. The last one is practical Byzantine fault tolerance. This is an algorithm, again, similar to the other ones, and it shows that you can get correct consensus if no more than a third are malicious. And this is basically similar to the other two, but this is the one that's widely used. So Bizcoin, Hyperledger Fabric, Hyperledger Aroha, these are all, and actually Docker Compose and parts of Kubernetes are using PBFT to get agreement. And so it's similar to the other two. You have validating peers that elect a leader. The leader coordinates what state gets committed, and then the peers will then distribute and replicate that state that's been decided upon. Okay, I'm going to skip the details of PBFT except to show you this. This is the amount of message exchanging that goes on the back end in order to basically guarantee consistency while moving the state along. So there's a lot of message passing to do the commitment protocol. Okay, there are variants to all of these things. Tangaroa, Tendermint, redundant Byzantine fault tolerance, and then Ripple. These are all things that are being proposed for blockchains. So either permissioned or public. You'll see that a lot of the blockchains, they're very similar to each other, but the big thing they differ on is how they get consensus. And this is important because when you talk about blockchains, you want high throughput. You want consistent agreement with high throughput. And if you look at the number of transactions a blockchain can actually support, it's really low right now. And so there is a race to basically get the most consistent, highest throughput backend blockchain possible. And this is what they're doing. They're looking at the theoretical foundations of distributed consensus, and they're trying to get to the sort of the maximum with that. So this is why I'm presenting it, but I'm not going to actually teach the underlying parts of this. Okay. The next thing I want to talk about is Byzantine consensus with weak consistency. And I'm going to talk about the Nakamoto consensus. So this is the consensus that Bitcoin uses. And we'll go back to the impossibility result. Consensus is impossible in an asynchronous network with a deterministic protocol. And basically what this, Satori does is he tweaks both of them, assuming that Satoshi is a he. No one knows the gender of Nakamoto. So he basically, I'm going to assume it's a he, tweaks both parts to get consensus. So the algorithm makes a strong synchrony assumption, meaning that, and this is a reasonable assumption on the internet, where it's rare that the network becomes partitioned. So that's the first assumption. But if that assumption fails, then you hedge the failure of that assumption using a randomized protocol, meaning that the consistency of your state will be sort of driven by some randomized protocol. And so effectively, the consensus algorithm assumes that you have replicas with very tight relay links. That means they're highly connected, and one state change that's been agreed upon will get replicated almost instantaneously to all the participants in your protocol. That's the first assumption. So in this case, the delay in propagating new blocks into your state should be more than an order of magnitude smaller than the creation of new blocks. And in this case, the delay assumption of propagating blocks is around 10 seconds. So this was engineered this way. So I'm going to assume a propagation delay of 10 seconds, And I'm also going to assume that adding new blocks will take 10 minutes. So this allows me to say everyone has agreed onto the previous block of the blockchain before I allow another one into the system. And it gives me hopefully a 9-minute window to reject double spending transactions. So this is the assumption that you're making. And so if you look at the Bitcoin algorithm, the time for creation between new blocks is done by a randomized proof of work hash puzzle done by the partial hash collision that we talked about last class. So that's why that delay has to be long. Okay? And then because technology is always going to improve, you have to adapt the puzzle to make sure that you're always achieving 10 minutes. So initially, I forgot how many zeros were in the blockchain. Was it 18 zeros? Initially, that was like under a dozen zeros was the hash puzzle. But then because people started building custom hardware to solve the Bitcoin hash puzzle, you see that number of zeros start to increase as the hardware has been made more efficient. Okay. So this is a mechanism that's used by most of the public trustless blockchains. You have this bounded asynchrony where the time to create a new block is larger than the propagation time for a newly accepted block. Okay, so that's what the Bitcoin algorithm is. And a block in Bitcoin has all of these things that we talked about last class in order to be used as a valid block in the blockchain. So there are some issues with doing this. The first issue I want to highlight is the power consumption needed to run this blockchain network, the Bitcoin network. So this is a graph of the number of terahashes per second being performed on the Bitcoin network. And you look at this is 6 times 10 to the 19 hashes per second. Now, this is all it's doing is that useless computation that we were doing yesterday. So this is what it leads to. These are pictures of mining operations in China. You have whole server farms. Look at all this hardware and all the electricity that's involved in running the Bitcoin network. And so this is the power consumption, the estimated power consumption of running the Bitcoin network. And if you look at the terawatts involved, this is an environmental disaster. So if you care about global warming, you get off of Bitcoin is what I would suggest. So there's an ethics problem here, right? And this is especially the case because there's a lot of illegal transactions being done using Bitcoin. So for me, this is a conundrum, right? We have basically the technology that people are pinning the future of financial networks on that's basically causing all of this resource consumption on the planet. And so one of the things that people are talking about are alternatives, and that's what Ethereum is looking at, because Ethereum also has a hash-based puzzle. So this is an important area of research. Another issue is the hash rate distribution. So we saw all of those mining operations. If you look at who controls the mining operations on Bitcoin, you can see basically 5 mining operations get you almost 2/3 of the entire hash rate that exists. So those are the folks who are controlling the ledger effectively. Similar to that is Ethereum. So the similar players are also dominating the mining pools in Ethereum. This motivates something like Monero. So Monero is looking at a proof of work algorithm that resists parallelization, and it allows any computer to potentially find a solution. And so if you look at their algorithm, it requires less energy consumption to use. But because it sort of evens the playing field amongst regular computers like the ones in front of you versus ASICs like you saw in the previous, because of that, you have cryptojacking on the rise. So if you ever hear on the news, you have cryptojacking malware. Basically what's happening is if you have installed some malware onto your laptop, it's basically going to try and mine Monero because the price of Monero has gone way up, and as a result, the amount of malicious sort of computers that are being used to hijack that has also gone up. Okay, so there's an estimate that 4% of the Monero is mined by malware bots. And so this is actually being used to replace ransomware. Because ransomware, it's hard to monetize ransomware as it turns out, because most users don't have a Bitcoin wallet. So this is actually a more effective way of monetizing a machine that you've compromised, just as an aside. Okay, so one of the alternatives to using hash-based proof of work is to use something called proof of stake. So the idea here is that instead of having mining, you have validators, and validators are trusted to randomly select the next block to insert onto the blockchain. And they're trusted because they have put up some collateral. I'm going to put up some collateral, I'm going to propose a block to be inserted, and if everyone agrees that that's a valid block to insert, I'll get my collateral back. But if I propose a block to be inserted, and people are like, hey, you know, that's got something going on, and they don't accept that block, then the collateral is taken away. So this is more of an incentive-based mechanism for ensuring proper behavior. Okay, so that's what I just described. Typically, there is some probabilistic election involved to basically choose the next validator based on the amount of stake that they have staked into the network. So one of the algorithms is this coin age selection, where you take some coins and you commit it as collateral, and then based on the number of days that those coins have been committed, you will be selected probabilistically in preference to other potential validators. Okay. And so in order for you to attack a proof of stake system, you have to hold 51% of the stake to actually shift the state reasonably. And if the market cap, this is old, this is from last year, if the market cap of Ethereum is 38 billion, then the notion is to do a 51% attack, you would have to have half of that. And so nobody has half of the Ethereum on the Ethereum network. So even if you had 0.01% of the Ether, this attack would cost millions. So this is the thing that's being proposed for the beacon chain, which is after this Istanbul hard fork in Ethereum. So they're trying to shift Ethereum over to this proof of stake. They couldn't do the whole thing, though, because the miners involved were raising hell. But this is one of the proposed improvements after the Istanbul fork. This is used in several other systems as well. There are some variants of this proof of stake idea. There's this delegated proof of stake, which acts basically like Congress. Like you take your coins and you vote for a delegate, and that's the delegate that is going to insert blocks on the blockchain on your behalf. You're going to vote for a delegate, and then the delegate is going to get randomly selected, is one of them. There's this leased proof of stake, where this is like a mutual fund. You give your you lease your coins to some trusted entity, and that trusted entity will then be used, will insert blocks onto the blockchain, but you get a block reward. Like if you're doing the work to get all the transactions, validate them, and insert them into the blockchain, there's going to be a reward for that. And then the idea of leased proof of stake is that that reward will then go out to the people who have leased their coins into the protocol. And so you have an incentive system for people to not only allocate their coins to a trusted entity, but for that trusted entity to act faithfully on their behalf. Because then that's the only way that that entity can make money off of mining as well, or validating. So there are some issues with proof of stake. The first issue is nothing at stake. This is a problem where there's no incentive in the proof of stake system to behave properly. So without any stake, the user, if users don't have a stake in the network, then they can vote on everything being valid to increase their chances of a reward. And so you need some way of penalizing participants for either double voting or hedging for a profit. The other problem is this long-range problem, where all the early adopters of a coin have much more power than a newer participant. Because the earlier you get onto a network, the larger your stake typically is. And the attack using this is to, because you have a blockchain and all of the points in that blockchain are valid states, then you could revert the chain back to an earlier state where you had all of the coins and then start mining from there. And as soon as you can get that chain to be longer than the current chain, then you have basically hijacked a whole bunch of transactions. You've basically undone the chain. Okay. So you need some other way of preventing that kind of attack. So limiting the growth rate so that when you go back in time and try and build a chain that goes parallel, limiting the growth rate so that it can never catch up would be one way of doing this. Or having some kind of weak subjectivity to choose the legitimate chain, even though the malicious one is longer. So rather than always going with the longest, you have some other way of determining what the valid state is on the blockchain. But this requires a centralized authority, which is what blockchains are trying to avoid. So you have that issue. Okay, skip that. The next kind of consensus protocol is proof of elapsed time, and this is what Sawtooth uses. And this is typically for permission blockchains. And in this case, trusted hardware elects the machine that will validate the next block. So the algorithm is that each node has this trusted execution environment, the SGX. The trusted hardware generates a random elapsed time, and the node will wait that elapsed time. And as soon as that elapsed time expires, it will actually try and add the next block. And the node with the smallest elapsed time will always win that race to insert that next block, and that'll be the one that's allowed to insert. Okay. This puts the trust in Intel SGX, but this is what's used in Hyperledger Sawtooth. Okay, so this is a picture of it. So you have a bunch of nodes. These are the validators. And then they each generate a random number. And then the lowest random number, this one, wins. So it's got the lowest wait time. And so it creates the block and then, well, it validates it and then inserts it onto the blockchain. Okay, another system is proof of capacity. So this is proof that you have a big disk where you can store a large data set, and then those who can navigate that data set more efficiently or quickly will win the race to insert the next block. And this is used in Burstcoin. Another system to elect the next block, the next miner, is proof of burn. And in this case, miners will basically send some currency to an unspendable address, like address 0 on the blockchain. So if you can show me that you just burnt some of your cryptocurrency into 0, I will let you mine a block, and then I'll give you a reward for successfully mining it that hopefully will allow you to recoup what you just burned to an unspendable address. And this is a sort of a proxy to say, hey, you know, I'm trying to spend money to keep this network secure. And then because you're doing that, because you're in good faith burning some coin, you'll get elected and potentially reap a reward, is the idea. So these are the places where it's being used. And then I'm going to end with a comparison of all these things and where they would be used. So you have a blockchain, and you have all these different ways of achieving consensus. You have the voting-based algorithms, which are the BFT algorithms. These are not very scalable just because of the number of message exchanges that are going on between the replicas. They're vulnerable to Sybil attacks, but there are no issues with forking. So forking means having multiple consistent states and having to choose from them. In the BFT protocols, you have one consistent state all the time. So this is really good for permission blockchains that require strict consistency. So this is where all the financial tech stuff is being based upon BFT protocols. Then you also have the lottery-based algorithms. These are scalable in terms of achieving consistency. They're resistant to Sybil attacks, but then they have this forking issue. And we'll talk about the forking issue when we talk about Bitcoin in the next class. This is good for public blockchains because you have Sybils on a public blockchain. Okay. So that is basically a rundown of consensus protocols and the major ones that are being considered for both public and private blockchains. Are there any questions about distributed consensus? All right, I'm going to give you the rest of the time to work on the Hyperledger stuff. Yeah.